Hello everyone and welcome to Valiant Tech World. Today we are gonna talk about linear regression and we will start by describing a problem, then we will describe how we can solve this problem with linear regression, evaluate the results, and then at the end discussing the solution found. Imagine that you just bought an electric car. You have used it to go around in your city, but now you are planning to do a long journey to another city. You know that when you use it in your city, you do not need to worry much about battery usage, because the battery can last for the full day and then in the evening can be recharged. However, with a long journey, you want to make sure that a fully charged battery is enough to reach the other city, so that you do not need to stop to a charging point. Now, imagine hypothetically that you are trying to obtain this information, but you cannot find it anywhere, so that the only thing left to do is to collect data in order to make a prediction on the battery usage. So you start to go around the city for your normal routine and start collecting the distance traveled and the related battery usage. For example, you go from home to office in the morning, so by driving for 20 kilometers, then the battery usage is 8.5%. Then after work, you go from the office to the supermarket. Again, you collect the data, and in this case, the distance traveled is 10 kilometers, and the battery usage is 4%. After the supermarket, it is getting late and you decide to head home, but before you want to stop to the park, and here the distance covered is 50 kilometers, and the battery usage is 21%. Then you were almost going home, but you forgot to buy the ice cream, so on the way home you stop to an ice cream parlor and again collect other data, which in this case is 37 kilometers and 16% of battery usage. Once you reach home, you start to look at this initial data and you can find almost a proportional relationship. So you decide to collect more data over the next days and use a linear regression to fit this data. The main goal is then to find the best coefficients of the function which needs to describe the collected data. Linear regression is used to find linear functions, and a line in a single dimension case has two coefficients, which we can call m and b. M modifies the slope of the line, while b is called intercept, and is the value of the output y when all the explanatory variables are equal to 0. In this case, the only variable is x, which is the distance traveled, while y is the associated battery usage. As said before, the main task in linear regression problems is to find the coefficients which, in this case, are able to create a line where the difference between the collected data and the line is as small as possible. These differences are called residuals, and they need to be minimized. This problem can be solved by using a procedure called ordinary least squares, where the sum of all the squared residuals mentioned before are minimized. The first formula shows the linear equation of a single data point I, where it is added also an error term, which takes into account all the variation of the output which are not associated to the non-input variables. The idea, as you can see in the second equation, is that the squared residuals are summed together for all the data points, and by finding the optimal m and b coefficients, this final sum can be optimally minimized. Or in other words, this final sum of squared differences between the predicted and observed values can be minimized. Note that the m and b coefficients found are estimates, so we call them respectively m hat and b hat. However, for the rest of this discussion, I will simply call them m and b to simplify the notation. Here you can see that the solution of the problem has a closed form, which practically means that by using the equation you can directly find the coefficients. So as long as you know the inputs and the outputs and then calculate the mean of the inputs and the outputs, you can find the value for m and the value for b. I will do a different video where I will go through the steps to obtain these formulas, so if you are interested, stay tuned. But for now, it is just important to understand that given a set of points and their averages, which are written in orange, it is possible to solve this problem by using these formulas. The linear regression problem can also be defined for more than one independent variable, and the equations are typically written in matrix form. For a generic point with output yi, there are p different input variables, and each of them is associated to a specific beta coefficient. And then there is also the coefficient beta 0, not associated to any variables because this is the intercept. Given that there are n data points, y is a vector of n by 1 dimensions, and also the error term, epsilon, is a vector of n by 1 dimensions. On the other hand, beta, as previously mentioned, is a vector of p plus 1 by 1 dimensions, where p is the number of input variables, and then we add the intercept. For the data, this is a matrix of n by p plus 1 dimensions, given that there are n data points, but for each data point, there is a multiplication for the beta vector of coefficients, which is p plus 1 dimensions. You can see that in the matrix, one column is all ones. That is the intercept column, which multiplies the beta 0 coefficient. This is a compact way to include the intercept in the input matrix, but the beta 0 does not multiply any other of the p inputs, given that every time it is only multiplied by 1. The ordinary least squares defined in matrix form is similar to the one-dimension case. The first equation shows how the problem is formally posed, and that is essentially the same equation used previously, where the sum of all the squared residuals is calculated and then minimized. But in this case, the aim is to find a vector beta with all his p plus 1 coefficients. Also, this solution has a closed form, and you can see that below. As I said previously, I will do another video where we will go more in depth into the equation mentioned here and how to obtain these formulas, so stick around for details. The linear regression problem can be evaluated with regression metrics. Here I'm showing the formulas of some of the metrics typically used for regression problems, but I have done another video, which you can find in the description below, where I provide more details about these formulas. So go check it out if you are interested in them. To summarize, these formulas provide a single number which tells how good the function fits the data. Smaller number, better fit. And the best possible value is 0 for all the three metrics. The metric that we will use is root mean squared error. Another metric that we will be using today is r squared, and also this one is defined in the video mentioned before. The metric is used for linear regression problems and provides a value typically between 0 and 1, where 0 is the worst and 1 is the best. The metric tells the proportion of the variance of the dependent variable that is explained by the independent variables. If the inputs can explain most of the output, then the value approaches 1. Otherwise, if this is not the case, the value goes towards 0. If you wish, go and check out the video on regression metrics for details and examples. The link is in the description. Now, let's see the performance of the linear regression on some training data. The training data are randomly generated points with a distance between 0 and 140 kilometers. The actual coefficients set by me are 3 for the intercept, because we consider a case where initially the battery drops faster the first few percentage, but then it stabilizes. And then 0.4, which is the coefficient linked to the distance covered. This is obviously positive, because more distance is traveled and more battery is used. Some noise is also added to the data points to take into account about other factors that are currently not considered in this regression. Using the closed formula shown before, then the estimates are 2.58 and 0.39, which are quite close to the actual coefficients. The root mean square error is quite small at 2.88, and the r squared is 0.9644, which is close to 1. This is typically expected on the training data, given that the regression line is fit on this shown data. Now we need to test it on data not seen before to check how the methodology performs. On the testing data, the root mean square error slightly increases and the r squared slightly decreases. This is expected because these are not data points seen before and we are using a line obtained with the training data. However, the performance are mostly the same and this shows that the function is a good fit for the data. Assuming that we know that to reach the other city we need to travel for 200 kilometers, then we can use the function to get a prediction of how much battery we are expecting to use. In the plot you can see the blue point is the expected battery usage at that specific distance traveled. So now you know that you are able to drive to the other city without the need of recharging the battery because it will use around 80% of the battery. This is a simplification. It is important to remember that just because the points are locally linear in the part used to train the model does not mean that they will also be linear in other places. This is an assumption and that's why it is good to have as many data as possible close enough to the point of interest, so that the chances that the estimate is not a good one decrease. Let's repeat the test by adding another factor, which is speed. In this example, also speed affects the data and increases the battery consumption. And if you drive faster, you use more battery, and for this reason, the coefficient for speed is also positive and set to 0.2. Let's assume that we are not aware of this other factor and we are simply fitting the data using the same two coefficients that we were using before, the intercept and the distance. Now, in order to compensate for the missing variable, the intercept becomes almost 14, while the distance variable stays overall the same. The root mean square error now increases to 4.38 and r squared decreases to 0.92. And this is expected given that there is a variable that we are not considering and we are using a function with lower dimensions to explain the data. By including an additional factor which consumes battery, then obviously the battery usage increases, and doing 200 kilometers seems still possible if the data continue to be linear, but the consumption increases from 81% to 91%. Let's now consider also the speed variable in the regression. So you link both the distance and the speed to a specific battery usage. Now the function is three-dimensional because x and y are the two variables and the new axis z is the battery usage. You can see that the estimates of the three parameters, which are intercept, distance and speed, are close to the actual values. The function is now a plane and the data points are close enough to this plane. Given the good fit, the root mean square error decreases while the r squared increases again, because we are able to use this additional information to obtain better predictions. Also in this case, 200 kilometers seems possible, however it depends, because it is not anymore a single value. Given that the distance is fixed, but the speed is your choice, you can go from 87% to 99% of the battery use. This means that the trick to reach the other city in this example is to drive slow to have some battery left. This again assumes that the data are still linear around 200 kilometers, and if that is not the case, well, you might want to bring some solar panels and a book to read just in case. This is it for today. If you enjoyed it and found it useful, please click the like button and subscribe to this channel. Thank you for watching.